So I'd like to pick up where Carlos Lopez Vasquez left off in terms of factors affecting EBPR and continue on with some additional factors that and how they affect EBPR within this part of the course. So, um, so what we're going to talk about mostly is factors including glycogen accumulating organisms, the carbon source and the COD per phosphorus ratio in the influent, and that impact on EBPR temperature, pH, dissolved oxygen and aeration, and the presence of inhibitory compounds. So that's a bit of a summary of the factors we're going to be looking at here in terms of its impact on EBPR. And I think there's been a lot of research done on each of these topics that will highlight a little bit here in terms of our knowledge and how that helps us operate EBPR systems. Okay, so basically, if we look at factors that impact phosphorus removal, we can sort of put them into some different categories. One is that we can look at factors that promote the abundance of POWs in the activated sludge community, trying to get a higher POW growth within that activated sludge. Ones that will impact factors that will impact the metabolism and kinetics of phosphorus removal, and then factors that will impact both the POW selection within the microbial community and then its activity, maximizing its activity. And there is a bit of there can be a sort of a long-term, short-term impact. It can sometimes take a bit of a longer period of time to select for different microbial communities, whereas some factors can have an immediate impact on the kinetic rates of phosphorus release or uptake and such. And so we're going to talk about each of those here. Okay, so first we'll start off with the presence of GAUs. So glycogen accumulating organisms. We had defined this previously, but basically just to recap, GAUs have a metabolism that's similar to polyphosphate accumulating organisms, but they rely solely on glycolysis of their internally stored glycogen as a carbon and energy source in order to take up volatile fatty acids and store them as polyhydroxyalkanoate. Okay, that's in the anaerobic stage. So, because these organisms take up VFAs under anaerobic conditions and they don't contribute to phosphorus removal, they're basically considered to be undesirable organisms because they can compete with POWs for that same carbon source. And if carbon source is limited, then that it can become problematic if GAU populations become too high and out of control. So there has been a lot of work looking at GAUs, and Campylobacter and Difluvicoccus are two well-known groups of GAUs that take up VFAs such as acetate or propionate. And we'll talk a little bit later on as well about some of the different operating environmental conditions that were studied to identify, the role of carbon source, pH, temperature, COD to P ratio on these kinds of communities and their impact on EBPR. Okay, so that's just a little bit about GAUs. And accompanying this, I want to talk also about the conventional. So those are the conventional POWs of Acuminobacter, conventional GAUs of Campylobacter and Difluvicoccus, but there's also fermentative POWs and GAUs that was brought out. So fermentative POWs like Tetrasphaera, we brought it a little bit in the microbiology discussion. There's also fermentative GAUs that have been identified, known as micropurina. These have been found in full-scale EBPR plants in different locations. And they've also prompted a rethink in terms of our understanding on how the competition between POWs and GAUs works and its effects on EBPR stability. So basically, if we think about conventional POWs and GAUs relying on VFAs, they take up VFAs, then other fermentative POWs and GAUs can contribute towards generating those VFAs. And that's what Petrosphere and microbuena can potentially do. So, so these organisms can contribute towards VFA production. Other heterotrophic organisms also can provide VFAs through hydrolysis and fermentation as well. So if we look at the fermentative POW and GAU, Nielsen et al. Proposed that a moderate presence of POWs could in fact be a positive sign for efficient EBPR because it indicates a presence of excess organic substrate that can support that supports the growth of POWs. Basically, that POWs will consume the organic substrates, and then GAUs will effectively consume what's left over. And so fermentative POWs and GAUs, they can grow under anaerobic conditions as well as aerobic conditions. As they're fermenting, they can have a little bit of growth anaerobically. And so this can provide them a little bit of an advantage under certain situations over classical POWs and GAUs in terms of their abundances. So the Danish wastewater treatment plants, they employ a lot of the side stream processes where you get a lot of dominance of these kinds of organisms. And so that's something that can interrelate with the classical POW and GAU phenotype. So I think one thing to keep in mind is when we think of fermentative POWs and GAUs producing substrates for other POWs and GAUs, basically then these fermentative organisms, they can contribute towards basically this VFA generation. And whether or not the fermentative organisms themselves contribute towards phosphorus removal, they can have a positive impact on, say, conventional POWs like Acuminobacter, providing carbon sources to them. So that can be a potential advantage. So, so there's different ways to look at these interactions between POWs and GAUs. Okay. So with the influence COD to P ratio, so this is one sort of influent characteristic, you can say, of how much COD do we have present in the wastewater influent, how much phosphorus do we have present. A number of studies have shown that high phosphorus presence or low COD to P ratio leads favorably to the growth of POWs, whereas a high COD to P ratio or low phosphorus in the influent can favor the growth of GAUs or a GAU-like metabolism. And one thing I haven't mentioned so far is basically we have different groups and organisms that are POWs and GAUs, but it should also be pointed out that Acuminobacter, for example, a well-known POW, can potentially perform a GAU-like metabolism with these same organisms. Okay, so these Acuminobacter can use glycogen as a main energy source, driving VFA uptake and not favoring that polyphosphate cycling, which leads to phosphorus removal. So that is something to sort of watch for, as well as just the microbial community itself too. So so that is something that the COD per phosphorus ratio in the influent can impact. Okay, so at high COD to P ratios, that intracellular phosphorus content is lower, and so that favors that glycolytic pathway, that favors that GAU-like metabolism, and that results in a lower phosphorus release per carbon consumption ratio as COD or as VFA or whatever. That can have a direct impact on how much P release you're able to see. Okay, so effectively you can have phosphorus limited environments, right? So, so this has a direct impact on the stoichiometry and kinetics of EBPR, and basically to comply with effluent discharge limits, we should try to maximize how much of the influent COD goes towards POWs. Okay, so oftentimes that influent COD is limited, and in those types of situations, it can be very important to try to drive that POW-like metabolism. Okay, so through the growth of POWs and that P release and uptake type metabolism, designing and aiming for that is an important then objective in terms operationally speaking. Okay, so and so the COD to P ratio that is in the influent can have an impact on this. Okay. In addition to the COD to P ratio, the type of carbon source present in the wastewater influent can also have an impact. Okay. So, um, so we talk about volatile fatty acids. Acetate and propionate are two prominent carbon sources of volatile fatty acids. There are others as well that can be produced, like butyrate and valerate, but acetate and propionate are quite prominent. Glucose and other sugars can be a potential carbon source for POW activity. Lactate and other alcohols, and also molasses addition in full-scale plants in fermenters, for example. These are some carbon sources that have been examined in the literature. These are just some examples, I would say, of the types of carbon sources that have been looked at to try to help drive EBPR. So, importantly, in terms of the type of VFA, acetate and propionate, it's been found that different POW and GAO organisms or strains have different preferences and affinities and uptake rates for carbon sources, being acetate or propionate, for example. So it's been found that Campylobacter has a clear preference towards the uptake of acetate over propionate, whereas Difluvicoccus gauze, which belong to the alpha proteobacteria, and this was a study of mine from 2005. But it was shown that these organisms have a clear preference for propionate as compared to acetate. Okay, so in contrast, Acuminobacter POWs can take up both acetate and propionate at comparable rates under anaerobic condition. So this implies that mixed acetate and propionate carbon sources can lead to lower GAO growth and more efficient EBPR when you have them present in combination. Okay, so having both acetate and propionate sources can be advantageous towards a stable EBPR. Okay. So, in terms of other carbon sources like glucose, there's been a bit of contrasting messages within the literature, but there's reasons for that. Some studies have shown that glucose can lead to the deterioration of EBPR by organisms outcompeting POWs like GAOs specifically, and through uptaking glucose and storing it as glycogen. Okay, so so other studies have shown that glucose can be fermented to VFAs in the anaerobic stage and some EBPR processes, and that results in stable EBPR performance. So overall, I think this comes down to really the design of the anaerobic tank and making sure that there's adequate fermentation time for compounds such as sugars or amino acids to be converted to VFAs to be fermented, and that can really dictate how the impacts on EBPR performance. So Tu and Schuler have shown that POWs, Acuminobacter in particular, have a higher substrate affinity for VFAs as compared to
or I think Difluvicoccus gauss in their study. And in that case, what you can see is that basically a Camelobacter can be better equipped to scavenge the available VFA produced in a fermentation in the anaerobic zone, either in a mainstream or a side stream scenario. If you have an anaerobic zone with a good fermentation time, that will favor the activity of POWs because they have that capacity to better scavenge low concentrations of VFAs. Okay. So that has a link then with what's been observed in the literature in terms of the uptake of something like glucose. And when looking at other sugars, say molasses has been dosed, for example, to pre-fermenters or fermentation tanks towards different organic acids, uh, particularly acetate and propionate. But you would when you do that and add molasses as a supplementary carbon source to help drive additional EBPR, what you end up with is effectively a mixture of carbon sources such as acetate, propionate, and other VFAs as well, which can be beneficial towards EBPR. And this has been shown in to promote EBPR. And there was work by Zheng et al., also Thomas et al., that have looked at this and have shown that basically with molasses you get quite a good variety of VFAs coming from it, which when looking for increasing the propionate fraction in your VFA, that can be advantageous for that purpose, as shown by these studies. And when dosing molasses into a fermenter as opposed to adding directly acetic acid or acetate alone, that can help promote good EBPR and more stable EBPR. And that's something that has been found in the literature, and it aligns very well with basically this idea that if you are favoring this diversity of carbon sources, basically you're favoring POW activity, POW growth and metabolism. Okay. So this can be strategies to do that. So there's other carbon sources in terms of the use of alcohols or waste organics to try to promote additional EBPR when carbon sources are limited. Again, this can be a common situation. So external carbon source addition to wastewater treatment plants to improve EBPR performance. Basically, this can incur, raw material costs and operational costs depending on the carbon source of choice. And so there's been a driver to look at alcohols such as methanol and ethanol for this purpose because they're cheaper. Glycerol also has been looked at. Glycerol is a byproduct also uh, uh, from from algal processes. For example, uh, in with glycerol, you can actually have this produced as a byproduct from from the production of bio oils coming from algal processes. So the use of glycerol has been investigated as an alternative carbon source, and other waste organics fall into this realm as well due to their basically the capacity to recover value from a waste organic and making this more economical as a potential carbon source to help drive EBPR. So these have been looked at as well, and there have been varying degrees of success with some of these different kinds of carbon sources in practice. And but oftentimes, if you can promote the fermentation of these kinds of waste organics, you can improve the utility of it as a supplemental carbon source to drive EBPR.
Okay, so then now moving on to the impact of temperature on EBPR. This is something that can be difficult to determine because temperature has an effect on all biological processes really within activated sludge systems. So that includes not just POWs, but it includes hydrolysis, fermentation, nitrification. All of those are impacted by temperature. So there's been a great deal of studies looking at the impact of temperature on EBPR, but some of those findings have been inconsistent. So some have observed improved EBPR efficiency at higher temperature. Some have found better pee removal efficiency at lower temperatures. So the differences in results here likely could be explained by, some of the different conditions, the different substrates, the different microbial community characteristics, some of the different approaches or measurement methods used in these studies that can explain some of this difference in terms of uh, what temperature can really favor EBPR. Okay, so the work of Brjanovic et al. Uh, also carried out some studies to look at the effects of temperature changes on EBPR stoichiometry and kinetics. So looking at short-term and long-term impacts on the short-term impacts on the immediate impacts on the stoichiometry and kinetics with short-term temperature change. A long-term change will promote a change in microbial community, and that also has a separate impact on EBPR. So what they found was that the kinetics of EBPR, so P release, P uptake, growth rates, they all increase as a result of increased temperature. So higher P release, higher P uptake, increased growth, all happened as temperature was increased from about 10 to 35 degrees Celsius. So Lopez Vasquez et al. Did analogous studies with GAUs, with Campylobacter GAUs, looking at stoichiometry and kinetics at different temperatures. And they found that GAUs were more likely to be competitive with POWs at higher temperatures. Um, so higher temperature, you can have faster kinetics. So EBPR can be helped by those faster kinetics at the higher temperature, but you also have an increased likelihood of GAU growth and that competition between GAUs and POWs for acetate to VFA uptake, for example, at high temperature it can occur more at those high temperature ranges of say 30 degrees or so. Okay, so this has then impacts on models associated with EBPR. So mathematical models of EBPR, we usually have stoichiometric and kinetic coefficients that that are dependent on temperature. Typically in ASM2, we have coefficients defined for 10, 20 degrees Celsius. Stoichiometric coefficients then are temperature independent usually, whereas the kinetic coefficients are what vary with temperature changes. And so there's these recommended temperatures for typical ASM2 models that are impacted certainly by the temperature of the wastewater in terms of applying these models. And also, what can be used is the results from these types of temperature studies have been used to provide correction factors within modeling endeavors to look for basically correcting how much P release or uptake will occur in EBPR. So these Arrhenius coefficients, these would be like a pre-exponential factor, this activation energy and the temperature with a universal gas constant. That would be effectively an Arrhenius coefficient with Arrhenius factors. That's a relationship that occurs and can be form part of then the models for EBPR in order to correct for temperature impacts. Okay, and that has been used in quite a large number of EBPR models.
Um, okay, so another factor that impacts EBPR is the pH. So Smulders et al., Philippe et al., they did tests with different pHs and have found that the anaerobic ratio of P release to acetate uptake tended to increase with increasing levels of pH. So the higher the pH, the higher energy is required, or higher ATP requirements exist for acetate uptake, and that has led to a higher phosphorus release. So that's the energy source, that ATP source for for acetate uptake, and so that is the explanation for why that pH why pH impacts the P released acetate uptake ratio in this way. So so in terms of other parts of conventional PAL metabolism, PHA production, glycogen consumption, substrate uptake kinetics, those were found to be largely unaffected by pH changes. Okay, so so basically, it was mostly had an impact on anaerobically. It had a big impact on the P released acetate uptake ratio, and and so this was something that was observed. So basically, it was also found then under long-term testing that low pH can favor the growth of GAUs, and while high pH would tend to favor the growth of PALs. Okay, so that was something that was also observed in tandem with this. So again, favoring the PAL metabolism with the higher pH, with a higher P release and uptake kinetics that are observed at higher pH. So this was interestingly observed recently by us with Tetrasphaera POWs as well, and basically then this higher P release and uptake increases as a function of pH then is basically favorable towards not just the conventional POWs like Acuminobacter, but also the Tetrasphaera POWs. And so that can provide then synergistic benefit potentially for for EBPR processes that have a high number of the Tetrasphaera POWs. So, so that's basically a summary of the impacts that pH can have on PAL on PAL metabolism. Okay, and so what's been done is that so a combination of operational factors like what is the carbon source, acetate versus propionate, what is the pH, is it 6, 7, 7.5, 8? What is the temperature, 10, 20, 30, so low, medium, high. So what you can do is um, look at the combination with mathematical models. You can employ mathematical models to predict what will be the impact on POWs versus GAUs in terms of their basically what combination of conditions will lead for uh, GAUs to grow and what will lead to POWs to grow. And that's something so published by this example is shown by Lopez Vasquez et al. And this was a study looking at the impact um, uh, of integrated POW-GAU models and the impact that acetate or propionate only, combinations of acetate and propionate, and then low or high temperature pH had on the microbial community. And what was shown here was that basically under low temperature situations, it would be very rare to ever come across a situation where you would have a growth of GAUs. Okay, so low temperature definitely will under regardless of the other situations, tend to favor POW growth and metabolism. Um, Whereas intermediate range, so maybe 20 degrees Celsius or so, um, it was mostly the extremes. At low pH, certainly was worse, and the extreme of carbon sources, whether it was all 100% acetate being fed or 100% propionate being fed, that tended to lead to um, these different gal groups, basically the alpha proteobacteria gals or Competibacter gals, that tended to lead to a mixture of POW and gal growth in some of those situations. But the other situations you'll note with a mixture of carbon sources, this tended to lead to only the growth of POWs, so POW dominated growth and metabolism. So this sort of reinforces what we were saying earlier when it comes down to different carbon sources and different factors, that the extremes of acetate or propionate alone would be less favorable towards a mixture of VFA sources to promote EBPR and to promote POWs. And this is something that in practice in full-scale wastewater treatment plants you often observe, because if you're doing a fermentation process, you will often have a mixture of acetate and propionate produced. If you're relying exclusively on acetate coming in the influent, you might have much higher acetate fractions then, because of a long retention time in the sewers can promote high acetate concentration. So then you might be left with a more extreme situation. But typically, in wastewater treatment plants, you do have a mixture of types of VFAs, acetate, propionate, and others potentially as well. And so that can actually be beneficial for POW activity and growth. So then at 30 degrees C, there was an increased number of situations, especially with the extreme of just 100% either acetate or propionate carbon sources. There was more commonly observed growth of Competibacter or Difluvicoccus gals over POWs. And notably, though, this could still be controlled at moderate pH levels, effectively at high temperature, with mixtures of carbon sources and moderate to high pH levels. So the combination of conditions does impact a lot on the microbial selection, and that has a direct impact on phosphorus removal performance, basically. So there's ways that combinations of conditions can reveal important information towards how we can potentially strategize how to control the process. Okay. So other studies have looked at impacts of other factors besides carbon source, pH, temperature. And one example of that would be the impact of dissolved oxygen concentration and just aeration time, okay, or aerobic fraction of the activated sludge process. So here uh, what we what Carvalheira et al. Showed was that basically when we had a low DO, that tended to favor the growth of POWs over GAUs due to their higher affinity towards oxygen. So POWs displayed a higher oxygen affinity. So they had a higher, not only do they have a higher carbon substrate affinity, but they have a higher oxygen affinity as compared to GAUs as well. So that means low levels of carbon source, carbon concentration, of oxygen concentration, POWs can be favored over GAUs. Okay. So again, that is consistent with how most wastewater treatment plants are run, but there's a driver towards minimizing dissolved oxygen, towards minimizing the amount of aeration just for energy concerns. So this can actually have a positive impact on the microbial community because it can help favor for POWs over GAUs when looking at lower DO levels. Of course, limiting the DO too low will impact the phosphorus kinetics as well. So there's a limit to how low that you can feasibly go before the kinetics of phosphorus uptake get too slow or of nitrification. So there are other factors that will impact the dissolved oxygen set point that you will choose, but provided that those factors are not being compromised, then lower DO can help favor EBPR. Um, also, basically, it has been shown that yes, and so a minimum aerobic sludge age should be ensured to ensure the growth of POWs. So we should have a minimum amount of aerobic time necessary to ensure good POW growth. But basically, also, Burjanovic et al. Showed that excessive aeration can negatively impact EBPR processes, and this is due to the depletion of intracellular PHA. Okay, so oftentimes under long aerobic zones or phases, that basically your PHA will be fully depleted, and this can lead to maintenance, basically POW cells relying on other storage polymers in addition to PHA for the energy needed for their own cell maintenance. And that's something. So if the PHA is fully depleted, they can then rely on glycogen or polyphosphate as a potential energy source there too. But this depletes their storage polymers. And doing so then basically will destabilize the process. And that's not good. That's not ideal for successful EBPR operation. So, and an example of this is also during extreme weather events or wet weather events when carbon source in the influent is diluted, oxygen requirements then should be reduced, aeration should be decreased to compensate for that. Otherwise, you can have basically a depletion of those intracellular storage compounds of POWs. That's the mechanism that really drives successful EBPR. Okay. So that's the point with DO and aeration. Another important thing that can impact the success of EBPR is the presence of potentially inhibitory compounds on the process. So one primary example that's been studied quite extensively is the presence of nitrite. So nitrite has been found to inhibit phosphorus uptake under both anoxic and aerobic conditions. And studies have shown that actually it's not just nitrite itself, but the combination of nitrite and pH, which can be termed as free nitrous acid or the acidified form of nitrite. That's the free nitrous acid. So nitrite but pH has an impact there as well. So the free nitrous acid concentration could was found to decrease P uptake rates during the anoxic phase very significantly, and also aerobically as well. Okay, so under anoxic conditions or aerobic conditions, basically the P uptake rates were very much inhibited by high levels of FNA or free nitrous acid, or the acidified form of nitrite. Okay, so so there's different sort of levels that have been found in terms of inhibitory thresholds for POWs for their P uptake, their aerobic P uptake, their anoxic P uptake, their anabolic processes as well, so associated with growth and so forth. So that is yeah, so that has been quite well studied in literature as well for its impact on EBPR. But there are other potentially inhibitory compounds as well. It's not just nitrite, but salts, for example, such as potassium and calcium, can cause phosphate to precipitate, and that means that it's no longer available to form polyphosphate, so being able to be taken up by POWs. So if you have chemical precipitation happening, then that's phosphorus that can no longer be stored as polyphosphate within POW cells, and that can be inhibitory towards EBPR. So in terms of chemical precipitation, yes, some caution is needed there when combined with EBPR in order to not inhibit EBPR processes as well, okay? Because precipitants can remove the polyphosphate, remove the phosphate, and then with less polyphosphate within POWs, that favors a GAL type metabolism, a glycogen metabolism, rather than a polyphosphate storage metabolism, and that is not positive then for enhancing then the biological phosphorus removal. Okay, so that's effectively then a summary of the impacts of these factors on the EBPR process. Again, I'd like to thank Alexander Wang for his contribution to this lecture, and I'd also like to thank you for your attention.